All right, we're continuing with the curve sketching example problems. We're on the 11th problem. I tried, my plan was to do these in increasing order of difficulty, but I accidentally I think I mixed it up. So they're not necessarily in increasing order of difficulty, but still, I'm going to do 15 of these videos. And so if you work all 15 of these problems, you'll get the full array of the skills you need and the practice you need to do curve sketching. Okay, so this is example problem number 11, and in this video, we're going to sketch this function here, x over the square root of x squared minus 1. Okay, step 1, the domain. So if we look here, so x can't be equal to 1, plus or minus 1, actually. All right, and really, it's more of the requirement here is that the absolute value of x needs to be greater than 1. That's the requirement. If the absolute value of x is greater than 1, then you won't be divided by 0, and you won't be taking the square root of a negative number. If the absolute value of x is less than or equal to 1, then you're going to have issues. You know, 0.5 squared is 0.25. 0.25 minus 1 is minus 0.75. 1 or minus 1 squared is 1. 1 minus 1 is 0. So that's the domain. The absolute value of x is greater than 1. If you have any x where the absolute value of that x is greater than 1, then it's part of the domain. Okay, now the range, we'll come back to the range later in the problem. All right, intercepts. Let's set x equal to 0 and solve for, well, okay, no. That's outside of the domain. X is equal to 0 is outside of the domain, right? We're not going to have, let's put the axes here. So we're going to go from minus 5 to 5, okay? And so if you, from 1 to minus 1, we're not going to have anything in this region here, right? That's outside the domain, which means that there's no y-intercepts. All right, but what about x-intercepts? So we set y equal to 0 and solve for x. There's no solution here. You might say, what about x is equal to 0? Well, no, because if x is equal to 0, you're taking the square root of a negative number. So that the x can't be equal to 0. It's outside the domain. So there's no x that's within the domain that would make this equal to 0. Okay, so there's no intercepts. All right, let's test for symmetry. Is this an even function? So all right. This is not equal to the original function, so no, it's not even. Is this an odd function? Minus y of x is equal to what? Okay, this is equal to, we can see here, this is equal to y of minus x. So this is an odd function. For any point x, y that's on the graph, the point minus x minus y will also be on the graph. It's symmetric with respect to the origin. Okay, what about periodicity? Is there some number p such that y of x plus p is equal to y of x? No, so this isn't some special kind of function that we need to check for periodicity. This isn't a trig function or an inverse trig function or a hyperbolic function, so we know it's not periodic. All right, next let's check endpoint behavior. So the domain here is, so if we could write this as minus infinity to minus 1, not including the endpoints, and then 1 to infinity, not including the endpoints, right? We could write the domain as, so minus 1 to infinity, and then 1 to infinity, like that. Okay, So the endpoints here are, there's four endpoints. We first want to take the limit as x, well, that's actually, hold on, I didn't write that correct. So it would be minus infinity to minus 1 in union with 1 to infinity. Okay, so let's take the limit as x approaches negative infinity of the function. Okay, so x divided by the square root of x squared plus 1. Okay, we want to store this as e. Okay, well, actually, that's not correct. It's square root of x squared minus 1. So, okay. Store this as e. Okay, so that's the function. Now let's take the limit as x approaches negative infinity of e. Okay, it's minus 1. All right. Now let's take the limit as x approaches positive infinity. Okay. That's positive 1. All right. But we want to check these. There's other endpoints here, minus 1 and 1. So what we're going to do here is say, what is the limit as x approaches minus 1, but so minus 1, but from the left, right? Not in general. It's not going to, there's not going to be a limit that's going to exist in general because there's no function in the middle. So, all right. So to do this, we say the limit of e with respect to x approaching minus 1 from the negative direction. Okay, yeah, minus infinity. Okay, now let's take the limit as x approaches 1 from the right of the function. Okay, so we'll do 1 from the right. Infinity. Okay, so that's the endpoint behavior. And so what we can see is we've got 2 horizontal asymptotes and we've got 2 vertical asymptotes associated with the endpoint behavior. Okay, so now we can draw in these asymptotes. So y is equal to minus 1 is going to be an asymptote. And then y is equal to plus 1 is going to be an asymptote. Can't really see that. So there we go. And then we also have vertical asymptotes at minus 1 and 1. So that would be here and here. There we go. Okay, next, critical points. We can come to let's come to a new sheet for this. Okay, let's start with the first derivative. So where does the first derivative of this function not exist or equal to 0? Okay, so dx. All right, there's nowhere where this is equal to 0, but perhaps there's a spot where the denominator equals 0. Okay. Minus 1 or 1, but that's an endpoint. So we're not talking about, when we're talking about critical points, so points where the first derivative is 0 or doesn't exist, and same with the second derivative, we're not talking about at endpoints. We're talking about within the domain. So there's no points where within the domain where the first derivative doesn't exist or is equal to 0. Okay, so none. All right, what about the second derivative? Okay, x. Okay, at x is equal to 0, this equals 0, but that's outside of the domain, right? So now let's solve for when does this equal 0. 1 or minus 1. So same idea. There's none. Okay, now this is a little confusing because we've got if we come back here, we've got kind of two different sections of the domain. So potentially, even though we don't have any critical points, we could have, like, let's say the concavity could change from here, this domain to this domain. But that's not going to be an inflection point, though, if that's the case. So, I mean, let's check this out. Let's do this. So if we look, we've got 0, minus 1, 1. Okay. Here's two regions, and there's nothing in this region. Okay. And then same idea here for the second derivative. So 0, minus 1, 1. Okay, and there's be nothing in here. Okay, so if we look at let's take a look at the first derivative. So dx, there we go. Okay, now let's evaluate this with x equal to minus 2. It's negative. Okay, what about x is equal to 2? It's also negative. So it's decreasing here and decreasing here. But maybe it could have, this could be decreasing, this could be increasing. All right, and for another case, let's say. So what does that mean? So we changed, the first derivative has changed signs, so we have like a local max or min? No. There's no, you can't have a local max or min unless it's at a critical point. There's no critical points. There's just two separate portions of the domain here, is all. And the second derivative, and for something like that, I mean, we'll see. Let's see what the concavity does. So the second derivative. Okay. With x equal to minus 2. Concave down. Okay. And then x equal to positive 2. There you go. Concave up. So what is it? Do we have an inflection point? We've changed concavity. The second derivative has changed sign. No. This is just, there's no inflection point here. We just have kind of two separate portions of a domain, and there happens to be different concavities. That's it. So there's no critical points with respect to the first, second derivative. There's no local maxes or mins, and there's no inflection points. Okay, so now let's sketch the curve. If we look at the endpoint behavior, so within this first portion of the domain here, this negative infinity to minus 1, as x approaches negative infinity, the function approaches minus 1. So we're going to be down here. We can't approach, you might say, well, can we approach, why wouldn't we be up here? Well, how are we going to approach minus 1? We can't, we could come into this region. It's not like this region is forbidden, but then we'd have an x-intercept. Like we need to, okay, well, another way to look at it is, as x approaches minus 1 from the left, we're going to negative infinity, right? We're coming down here. So how can we possibly have a curve up here and approach minus 1 as x goes to negative infinity, as well as approach negative infinity as x approaches minus 1? Like you can't, you just have to think about that. Like you might say, well, how do we know that it doesn't? So we're going to do this, right? We're going to say, okay, well, how do we know it doesn't? Let me redraw that. Well, how do we know it doesn't do this? Well, because then you'd have a local max. That's possible. You'll have functions that do stuff like that. Then you'll have a local max. We don't have a local max, right? How could we, we could do this. We could potentially do this. Well, first of all, we'd have an x-intercept. We didn't find an x-intercept. But then how are we going to do this without a local max? You see? So we know that there's no special points. There's no inflection points. We're concave down in this region. There's no inflection points. That's another thing, too. We know we're concave down over here. How could we be concave down and have a curve up here? I mean, but then you have to have a local max. So you could be concave down, but then you have to have a local max to do it like that. To have something like, no, because you'd have to approach this from the top, minus 1 from the top, you'd have to be concave up. We know it's concave down everywhere here. So this has to be the curve. Now, on the right side, we're concave up. Okay, so and as x approaches positive infinity, the function approaches positive 1. As x approaches 1 from the right, the function approaches infinity. So like that. Now, whenever I look at the actual graph, if I plot this in Desmos, it looks more of like that. Okay. But if you wanted to get the graph to graph it more accurately, you could have just taken, maybe you evaluate the graph, like plug into the function a couple of points in here. Maybe we could have done that. So get like a couple of points. That would have helped you to get the shape, right? We could have done that. Do everything we did here, but then when you go to, like, you could do that for curve sketching if you want to make it more accurate. Do everything we did here and that we do in every video. Do everything we did, but then when you go to sketch the curve, plug in a few points, random points, not critical points, just a few random points, just to guide you. All right. So now before we finish, what's the range? The range is going to be, if you look closely, the range is going to be minus infinity to 1. Or no, to minus 1. And then 1 to infinity, just like the domain. It's a coincidence, right? You can get any value from minus infinity, all the way up to minus 1, not including minus 1. And then you could go from 1, not including 1, all the way to positive infinity. But you can't get anything in between here. You can't get any y value in this region. Just like you can't input any x value in this region. And that's the graph.